Hello, welcome back to the CMSoft case study of fast simulation of heat transfer using C# and OpenCL. In the previous video of this video tutorial, we saw how to implement in OpenCL C99 code a code that will run on the GPU and that will map intensity values to color values. So, given an intensity T and a minimum and maximum value of temperature, this function returns a float of four component vectors whose components are the red, green, and blue, and alpha, the transparency values of the texture calculated from this intensity T. So the value that is returned by this function is a color value, which is mapped from the intensity T. Now we're going to get back to the heat equation, and we saw that we compute the values, the distribution, the temperature distribution inside the plate. We need to have the current values of temperature distribution so that we can compute what's going to be the distribution in the future, what's going to be U of t plus delta t. So we also know that in this we need the initial values, and we also can't compute the values of the Laplacian outside the bounds of the matrix. This means that in the boundary here, we need to know what is the distribution of temperature at all times. In this case, we're going to consider that the temperature in the top and in the bottom is fixed at 240. To the left, the temperature is fixed to 100, and here the temperature is fixed to 0 Kelvin or Celsius. So these are the boundary conditions. We need them because we can't extrapolate and get elements from outside the matrix. But the interesting part is that, for example, we could fix values of temperature anywhere inside the grid and create an entirely new problem that couldn't be handled analytically. And we could do that simply by, between iterations, we could go back and set some values of these cells to a given value of temperature that we wanted to have. So the discrete simulation, the finite differences method, is very versatile to handle different boundary conditions and initial values that we wouldn't otherwise be able to handle. Alright, so we now know that we need these initial values and boundary conditions, and we have all the resources that we need to present the results to the user. So now let's proceed to analyzing how we go about simulating the system. It's a very good idea to have in mind this picture here, because each cell is going to be accessed from an element of a matrix, and we're going to be using that trick of swapping matrices, swapping, in this case, vectors that hold the values, so we don't need extra memory allocation. So let's get down to business here. Our initialization, how do we go about initializing? So first of all, we define the minimum and maximum temperature. So minimum 0 to 250. We set the time step to 0.05 and the space step, that's the delta x, between pixels to 0.3. These are just arbitrary values. We start off with alpha of 0.8. We can configure this in the environment. So this is the OpenCL source. We're going to get back to this in a minute. When this class is initialized, we compile the code and retrieve the kernels here. These kernels are essentially the same. I'm going to show you the difference in a minute. Now, we need we need kernels to store our kernels, right? We need to get the image to the object, which is the texture that we are using to display the results to the user. We're going to create the values, an array, which is in fact is a matrix of values of heat, the heat distribution along the plate. And we're going to create OpenCL variables that will be stored in GPU memories, which will be the previous values of temperature distribution and the next temperature distribution. We'll be swapping these two as we go along. So I write to this one, then I use this as the source to compute the next values of this one. We also need to pass to OpenCL what are the parameters of our simulation. So we're going to use another variable for this, and I'm going to create the values in the host memory so I can copy the values to OpenCL, to the device. And this is just a variable to store the dimensions of the problem, the width and the height of the image. So how do we go about initializing this? Well, when the class is first loaded, the program is compiled and the kernels are retrieved. Then whenever a new instance of a heat transfer simulation is created, it has to receive a CLGL image, which is a texture created from OpenCL and retrieved from OpenGL. We already saw that in our case, the texture is stored in CLIMG. So here, when I'm creating a new heat transfer object, a new heat transfer class, I'm going to pass the texture that I retrieved from OpenGL to the heat transfer, so it knows to use this shared texture to update values and display the image to the user. So now let's get back to the code here. We need to store heat values, and this is a matrix that it has width, W elements, and age, W times age elements. This is a matrix stored in vector form, so that heat values stored in position ij, or heat values stored in position xy, is heat values indexed by y, which is the height, the y component, plus the image height times x. So we're storing this, we are storing the rows sequentially. It may matter for the problem you are trying to solve if you store in row major or column major order. But in this case, since we need to access all four neighbors, remember this picture here, since we need to access the central element and its four neighbors, in this case, it's not going to make a difference. So at this point, I'm setting the values in the left side to 100. So this is a boundary condition. I'm setting this boundary condition here. This one, temperature fixed at 100. Then I'm setting the top and the bottom of the plate to have 240, temperature 240. So these values here. See, this is the biggest value y can have. You know, since the dimension is CLIMG point height, y can only go up to CLIMG point height minus 1. And in this case, y is 0, so I just omitted it. Now I'm going to create two new variables in device memory. And I'm going to create them from these heat values here. So I'm creating two arrays in OpenCL memory, in device memory, in the memory of the GPU, which have the dimension width times height, and whose elements I'm going to access. The heat value, the value of temperature in position xy, is y plus x times CL image dot height. So I'm going to pass the size. I could retrieve from OpenCL, but I'm just going to pass them explicitly to make things a little bit more neat here, a little bit more clear. Okay, now I set dimension, an array of dimensions in the host code. I create a vector to hold the parameters of the simulation, which I'm going to write right here. We're going to see what the parameters are in a second. These are values like the time step, the step in space that the OpenCL code needs to know in order to run our simulation. Now I create the variable to store the dimensions of our problem in GPU memory, and I create a variable to store the parameters, the dimensions and parameters of simulation in GPU memory. Okay. Now, how do we go about stepping the simulation forward? Well, first of all, we're going to populate the heat parameters. So the first parameter I'm going to pass to the GPU, to OpenCL, to the device, is the space step, then the time step. I put here a delta t times 0.5 because I'm performing 2 steps per iteration, because I need, like I said, I need to swap the current and the next value of temperature, so I don't need to allocate more memory. So I do 2 steps per iteration, say. I pass on the alpha value, which is the conductivity, the heat coefficient, the maximum and minimum temperature of the simulation. So this is used to generate the picture. So remember, we're analyzing what is it that we do when we step the simulation forward. So we're computing the next value in time. And we let the user tell us how many steps forward he wants to compute. At this point, we acquire the image from the OpenGL. So we're saying, hey, OpenGL, stop using this image because we're going to operate using OpenCL now. Now we're going to step the simulation forward. We're going to analyze this kernel, these kernels in a second. But basically, see, there's the kernel heat step, and I use the previous value and write heat values, and then I swap. I use heat values as source and the previous values as the destination. So I don't need to allocate more memory. I can continue stepping forward doing this. And you can see that there's a last kernel here. So when the user asks for n steps, we're in fact executing 2n steps. That's what we return, 2n steps. But we don't need to write the image at every step, because the program is going to ask OpenGL to draw the picture onto the screen only after we're done with this n steps, or 2n steps in this case. So this last kernel is the only one that writes the image. So it's the same kernel with the difference that it writes the results to the image. I'm sorry. So the difference is that it retrieves the intensity values and writes the color representation into the image. Now, what do these kernels do? We can see that these are the parameters of the kernel, and the global dimensions are the width and height minus 2. Now this minus 2 comes from the fact that I'm not updating values in the top, in the bottom, left, and right. So the central value of the work item is going to be the value, the index ij of the work item plus 1. So this is just so that I'm not starting x at 1 and ending it at width minus 1. I'm starting at 0 and ending it at width minus 2. This is just for compatibility with OpenCL 1.0, because in OpenCL 1.1 and 1.2 I could use the global offset. Sorry. I could use the global offset to set this value. So this is just for compatibility. And after I'm done using the image, I release the image back to OpenGL so it can be rendered onto the screen. Now let's analyze this kernel. It receives the parameters of the simulation, the dimensions of the problem. Notice that I'm using constant memory space. This is one of the beautiful things of OpenCL, in my opinion, because you have explicit control of what variables you're going to put in what caches. So there is a constant cache that needs to go up to at least 64 kilobytes. Then there's a local cache, which is as fast as the constant, but it's not as not every work item can see it. This is a topic for another video tutorial. And so I'm allocating this to in constant memory, and the previous and next values of heat. The previous values I'm only going to read, so I use the const directive to tell OpenCL that I'm not going to modify these values, so it can use texture caches to cache these values. The heat values on the other side I'm going to modify, and I'm going to modify the image too. So in OpenCL you can either read or write to an image, you can't do both. In this case I'm just going to write. And so the order of the parameters are the delta x, the step in space, delta t in time, alpha, conductivity, and maximum and minimum temperature. So these are the values that are stored in that array. Now, here I get the x and y position of this work item. So if it were a for loop, I'd have a for x from 0 to width, and then a y from 0 to height, in this case height minus 2. So I'm just retrieving the identity of this work item. Now here's a little trick so that I don't have to multiply. I can save some multiplications here. I know that I'm going to access the heat value xy using heat values y plus image.height times x. So I'm going to compute image.height times x only once and store it in this ind here. Remember, this one is the height. The dimensions 1 is the height of the image. So since this code here of the kernel is going to be executed many times, saving this multiplication is an interesting thing to do. So like I said, we're going to modify the value at x plus 1, y plus 1. So this means we are modifying the value which is stored at y plus 1 plus img.height times x plus 1. This is the central value we're modifying here. So here I get the central value, which is exactly this, just that I'm just using this IND so I don't have to keep on multiplying by x. And since I'm multiplying by x plus 1, I need to add another height. So I don't need to multiply, I need to sum. Now I'm going to compute the central value. Remember from the formula, we had that the neighbors are summed, but the central value is subtracted twice. So this is subtracting twice the central point so that we can compute uxx and uyy. So the uxx is the central value, this variable cval, times minus 2, just like we did in the example, plus the central value at y plus 1 and IND, which is the value to the left of the pixel, and this is the value to the right of the pixel. We didn't divide it by the delta x squared yet. And now uyy is the central value times minus 2, and y at the top. See, this is not y, this is y plus 1 minus 1, y. It's the value at the top of the pixel, plus the value at the bottom of the pixel. Now we do a little trick here again. We need to compute delta x, 1 over delta x squared. So we compute 1 over delta x only once, then we square that value. And finally, we're going to update the central value. It's going to be the old value, which is this value here, see, the original value, plus parameters 1, which is delta t, times parameters 2, which is alpha, times the Laplacian. And now we have to divide by delta x squared, which we do here. This temporary variable stores delta x, 1 over delta x squared. Now we do the update to the next values, the central value here. Remember, this is just this value here. Written, we use a vector to represent a matrix here. I set the value. And here's the difference from the two kernels. If I'm executing the very last kernel, I write a color representation of this temperature intensity into the image. Otherwise, I just don't do it, because it's not necessary. I'm still, when it comes to the very last kernel, I'm going to write the output to the user. So the color of the pixel that I want to set, remember, I'm going to set it in position x plus 1, y plus 1. It's the value, the intensity value, and parameters 3 is the maximum temperature, parameters 4 minimum temperature. Then I get the float 4, which is a vector that represents the RGB alpha value of the color, and I set this color to the image using OpenCL write image f img. I write to the image using coordinate x plus 1, y plus 1, and I write the value of the color that the function that we wrote previously returned us. So after we execute this with global dimensions in the center, which is from 0 to the width minus 2, and y from 0 to the height minus 2, what we did is we updated the interior of the plate. We updated the values of temperature in the interior of the plate. So we performed one step forward in time. Overall, we're going to perform n steps times 2, because we need to swap the buffers here, the variables. Okay, so we now have a class, a C# class, in which we receive the image as the input, and we step forward in time. Now the last thing we need to do is to go back to our form. Let's see what our simulation code does. First, I set the mouse so that the user can translate the model. I tell the program that the simulation is running. I'm going to count the total number of iterations, and I'm going to start measuring time, just so I can count frames. Remember that our step function returned the number of steps we performed, so I sum that into the total number of steps, and I calculate how many updates we're doing per second. I get the total number of steps and divide it by the total seconds elapsed. And then I'm going to write on top of the screen the number of iterations per second. And I'm going to ask OpenGL to redraw the scene. And I'm going to do the application event so the user can stop the simulation. So let's see how this goes about. So we start with a 0, 0, 0 plate, and there's the colors here. There's a one initial step just to remove some rough edges and these things. Now let's see what happens when you click the simulation. We're going to start stepping forward in time. Now I can move the simulation. The simulation is running at 400 iterations per second. And we can see how the heat distribution evolves over time. So we get each of the pixels and we iterate them forward to compute the next value in time. So this is pretty nice. This is 400 iterations per second in a laptop computer. Using my desktop computer, I'm able to get to up to 7,000 iterations per second in a grid that is bigger than this one I'm using here. But the definition is pretty good already. Alright, let me stop the simulation here. So we did the analysis of the heat transfer code, how to initialize, how to step forward in time, and in the next video we're going to wrap up this discussion and have some comments on how to simulate other equations or how to create other boundary conditions. Thank you.